Hi, I'm Eve and welcome back to Tales by Eve. Today's episode is a little different. It's a journey, a conversation, a thought experiment that stretches across time, space, science, and imagination. I call it Cosmic Frontiers, Time, Planets, and Life Beyond Earth. It started with a question, something simple, but strangely haunting. What if time isn't even real? What if everything we know, memories, cause and effect, past and future, is just an illusion, a construct? In my search for answers, I wandered through theories of physics, discussions from brilliant minds, and yes, even the odd late-night Reddit thread. Some physicists argue time is a fundamental part of reality. Others? They say it might be emergent, something that only appears when matter interacts, like a shadow cast by deeper laws of nature. Then there's the problem of time, an unsolved riddle in quantum physics. How can time exist in one equation and vanish in the next? But that's just one side of the story. As we step beyond time, we encounter space, deep, infinite, and teeming with mystery. Thousands of exoplanets have been discovered, each one more alien than the last. Some are scorched on one side and frozen on the other, tidally locked in a cosmic dance with their stars. And yet, some scientists believe these planets might still cradle life, hidden in the twilight zones between fire and ice. I even fell down the rabbit hole of sci-fi writers imagining civilizations on those strange worlds, and the real science that might make them possible. We'll also explore something that sounds like science fiction: time travel. Could we travel into the future by riding the waves of gravity? Or is the past forever out of reach? In this episode, I bring together insights from 10 different sources, from theoretical physics to philosophy, from Wikipedia to whispered ideas in the depths of online forums, to build a tapestry of wonder that I hope will spark something in you. Curiosity, imagination, awe. So whether you're here for the science, the mystery, or just a beautiful what if, make yourself comfortable and let's begin. This is Cosmic Frontiers, Time, Planets, and Life Beyond Earth. And you're watching Tales by Eve.
Okay, let's unpack this. Today, we've got a stack of sources that take us on, well, a pretty wild ride. It really blurs the lines between science fiction and actual cutting-edge physics.
Absolutely. We're looking at some really fascinating stuff.
Yeah, we're talking about the real-world possibilities, or maybe impossibilities, of time travel. Then jumping light years away to the most bizarre, most extreme planets discovered out there.
And then capping it off with maybe the biggest question of all.
Right. Is time even real? Like fundamentally a physical thing?
It's definitely a journey from, familiar sci-fi tropes right to the edge of what we even understand about reality itself. These sources touch on some profoundly deep ideas.
They really do. So our mission in this deep dive is to navigate all this material, pull out the most crucial insights for you, and kind of give you a shortcut to understanding these pretty mind-bending topics.
Sounds good. Where should we start?
Well, where else? The ultimate sci-fi dream, time travel. I mean, we've all imagined hopping into a DeLorean or the TARDIS, visiting another era. It's just irresistible, that idea of traveling backward or forward.
It captures the imagination like few other things.
But let's be clear up front, like the articles really stress. Those machines, the TARDIS, the flux capacitor, they're just fiction. They're not really based on physics as we know it.
Yeah, that distinction is absolutely crucial because what physics actually tells us is, well, it's a split decision, isn't it?
How so?
Based on our current understanding, traveling into the future, that's not just possible, it's basically baked into the laws of physics. We see effects of it already.
Okay.
Traveling to the past, though, that's where things get incredibly difficult, maybe even impossible.
Right, and this all comes down to Einstein, doesn't it? His theories of relativity. That seems to be the core insight here. Time isn't this fixed, universal clock just ticking away the same for everyone, everywhere.
Exactly. It's not absolute. Physicist Emma Osborne points this out. Time can actually speed up or slow down depending on your circumstances. It's relative.
So how does that work? How can time change?
Well, relativity gives us two main ways time can get warped, let's say, causing time to pass slower for you compared to someone else. We call it time dilation.
Okay, two ways. What's the first?
Speed. If you travel really, really fast, like approaching the speed of light, time literally slows down for you relative to someone stationary.
Ah, the twin paradox. I remember that.
That's the classic thought experiment, yeah. Quantum physicist Vlatko Vedrel mentions it. One twin zooms off in a spaceship near light speed, comes back, and they've aged less than the twin who stayed home.
And haven't we seen like tiny real-world versions of this with astronauts?
We have. Scott Kelly, the astronaut, spent nearly a year on the International Space Station, traveling much faster than us on Earth. When he came back, he had aged fractionally less than his identical twin brother Mark on the ground. It's a real effect, just very small at those speeds.
Wow. Okay, so speed is one way. What's the other?
Gravity. Strong gravitational fields also slow down time.
Really? Like just being near something heavy?
Exactly. Near a black hole, for instance, time would pass incredibly slowly compared to far away. Osborne even makes the point that here on Earth, gravity is slightly stronger at your feet than at your head.
Wait, seriously?
Yep.
Yeah.
So technically, your head ages just a tiny, tiny bit faster than your feet.
That is wild. Absolutely wild. And this gravity effect, that pops up in movies too, right? Like Interstellar.
Precisely. That's a great example the sources mention. The characters near that massive black hole gargantua. For every hour they experienced, years were passing back on Earth, far from that intense gravity. That's time dilation due to gravity.
Okay, so speed and gravity can slow time down for you. Are there like practical uses for this?
Oh, absolutely. The biggest one, highlighted in the sources, is GPS, Global Positioning System. Those satellites orbiting Earth. Their clocks are affected by both factors. They're moving fast, so their clocks should slow down a bit. But they're also in weaker gravity than we are, which makes their clocks speed up a bit more.
Oh, so it's complicated.
It is. And the gravity effect is stronger. Overall, their clocks run faster than clocks on the ground. If engineers didn't constantly correct for these relativistic effects,
What would happen?
your GPS, like Google Maps on your phone, would be wrong by about 10 kilometers every single day.
10 kilometers a day, just because time runs differently up there.
Just because of relativity, yeah. It's essential to account for it.
Okay, so the big insight for future travel is you don't actually need a TARDIS, necessarily.
Not in the sci-fi sense, no. If you could travel incredibly fast or hang out near a black hole,
You'd experience maybe just a short time yourself,
days, weeks, years,
while maybe centuries pass for everyone else back on Earth or somewhere with less gravity. You'd effectively arrive in their future.
Exactly. Future travel is physically possible. The catch is you can't just turn around and come back to your present.
Right. And that brings us to past travel, which sounds much harder.
That's putting it mildly. This is where physics, as theoretical physicist Barak Shoshani puts it, kind of hits a wall. Future travel flows naturally from relativity. Past travel, it's way more speculative and honestly looks pretty unlikely based on what we know.
But are there any theoretical loopholes? The sources mention a few ideas within relativity itself, right? Like closed time-like curves.
Yeah, CTCs. Kurt Gödel, the mathematician, found solutions in Einstein's equations back in 1949 that mathematically described paths through space-time that loop back on themselves.
Well, like a time loop.
Essentially. But they're purely theoretical. We have zero evidence they actually exist in the universe.
And even if they did.
Well, there's no known way to create one deliberately, and as Vidrol and philosopher Emily Ablam point out, if you were on one, you'd just be trapped, endlessly repeating the same sequence of events. Not exactly practical time travel.
Okay, so CTCs are probably out. What about cosmic strings? Sounds very sci-fi.
It does. These are hypothetical defects, like cracks left over from the very early universe. In the 90s, Richard Gott suggested that if you had two of these massive strings moving past each other at near light speed in just the right way...
Let me guess. They might create those closed time-like curves.
Exactly. But again, huge problems. Theoretical cosmologist Katie Mack emphasizes: 1, cosmic strings are hypothetical, we've never detected any. 2, finding two of them and having them move just right. The odds are vanishingly small.
Seems like a long shot. Okay, third option. Wormholes. Everyone loves wormholes. Tunnels through space-time.
Yeah, wormholes are shortcuts. Vedrol confirms they are theoretically allowed by general relativity. They connect two different points in space-time.
But of all they, there's always a but, isn't there?
Always. Again, zero evidence they exist. If they form naturally, they'd likely be microscopically tiny.
Not big enough for a person or a ship.
Not even close. And they'd be incredibly unstable, collapsing almost instantly under their own gravity.
So how would you make one stable and traversable, like in the movies?
Well, according to Osborne and Vedrol, that would require vast amounts of something called exotic matter. Matter with negative mass or negative energy density.
Negative energy. Did that even exist?
We don't know if it exists in the form or quantity needed. It's highly hypothetical stuff. So making a traversable wormhole seems, well, let's just say it's far beyond anything we can currently conceive of, likely impossible.
Okay, so relativity's roots to the past seem blocked by either needing things that don't exist or conditions we can't create. What about the other big theory, quantum mechanics? Physics of the small. It's famously weird.
It is very weird. And it does have phenomena that seem time-bending, like non-locality or Einstein's spooky action at a distance.
It's entanglement, right, where two particles are linked.
Exactly. Measure one and you instantly know something about the other, no matter how far apart they are. Adlam confirms this is experimentally proven. It seems faster than light.
So could that be a way back? Some interpretations talk about retrocausality.
Yeah, the idea that measuring a particle now could somehow influence its entangled partner in the past. It's an attempt to explain the instantaneous link without breaking the speed of light limit.
Sounds promising.
Well, it's a fascinating idea, but highly debated. And even proponents like Adlam are clear. This is confined to the quantum realm, tiny numbers of particles. It wouldn't let you send, yourself or even a meaningful message to the past.
Why not?
Apparently, any attempt to actually check if you successfully sent information backward seems to paradoxically require destroying the record of sending it. Makes it pretty useless for communication.
Huh. Okay. So the bottom line on time travel, based on everything we've looked at.
The strong consensus from the physics sources seems to be future travel, yes, a consequence of relativity. Past travel, extremely unlikely, possibly fundamentally impossible with our current understanding.
As Barak Shoshani notes, maybe we need that deeper theory, the one that unifies relativity and quantum mechanics, to be absolutely sure. But for now.
For now, yeah. Back to the Future stays firmly in the fiction aisle.
Okay. Let's completely change gears. Forget bending time for a moment, and let's look at the sheer weirdness that's already out there in the universe, revealed by telescopes. Our sources dive into exoplanet extremes, and honestly, it's like a cosmic record book of the bizarre.
Oh, this is where it gets really interesting, I think. These aren't just planets. They're showing us the unbelievable diversity the universe is capable of. Things we never imagined.
Let's fire off some of these extremes. Just the locations. The closest one we know, Proxima Centauri b, is just over 4 light years away. Practically next door, cosmically speaking.
Yeah.
And maybe habitable.
Compare that to the farthest confirmed one mentioned, Sweeps 11, over 27,000 light years away. Still in our galaxy, but way out there. And rogue planets, not tied to any star. They could be billions of light years away.
And the sizes and masses are just all over the place. The lightest one found, PSR J0337 plus 17.5 in EB, is like 0.004 Earth masses. That's less than half the mass of our moon.
Imagine a planet less massive than our moon. And then you have candidates like CWWW9AB, maybe 36 times the mass of Jupiter, almost a star itself, a brown dwarf.
Size-wise, tiny Kepler 37b, smaller than Mercury, versus giants like HAPP 67b, twice Jupiter's radius. Just incredible range.
The density. Density is where it gets truly mind-bending for me.
Oh yeah, what's the record there?
There's a planet, GP Comet Berenices b. Its density is listed as over 185 grams per cubic centimeter.
Wait, 185 osmium, the densest element on Earth, is like 22.
Exactly. This thing is almost 10 times denser than osmium. It's so dense, the source suggests it might be made of strange matter, some exotic state of nuclear matter.
Whoa. Okay, what about the least dense?
Planets like Kepler 51b or WESP 193b. WESP 193b is described as being as fluffy as cotton candy. Its density is about 0.06 grams per cubic centimeter.
Less dense than styrofoam, a giant gas ball lighter than cork.
Pretty much. You
Right.
could theoretically float it in a giant bathtub, if you had one.
That's amazing. Temperatures must be extreme too.
Oh yeah. The hottest one listed, Kelt 9b, sizzles at over 4,000 Kelvin on its day side. That's hotter than the surface of many stars. Its atmosphere is literally boiling off into space.
Yikes. And the coldest?
OGLE 2005, BLG 390 pounds, a frigid 50 Kelvin. That's minus 223 Celsius, just unbelievably cold.
These extremes just keep coming. Fastest rotation. Beta Pictoris b, its equator spins at nearly 20 kilometers per second.
And WESP 127b has winds clocked at 33,000 kilometers per hour. That's just staggering speed.
Then there's brightness. One planet, LTT 9779b, acts like a giant mirror, reflecting almost 80% of the light hitting it. Super shiny.
While another, TRES2b, is the opposite. It reflects less than 1% of light, darker than coal. A pitch black world.
Age differences too, youngest and oldest.
Youngest mentioned is DH Tauri b, maybe only 700,000 years old. Almost as old as the universe itself.
And their years, their orbits.
Completely wild. One planet, JLX 07188 plus 3731b, whips around its star in 11.2 minutes. Imagine having over 46,000 birthdays every Earth year.
That's insane. And the longest year.
Gliese 900b takes 1.27 million Earth years to complete one orbit. Then you have planets with orbits so stretched out, so eccentric, they swing incredibly close to their star, then way out into the cold. And Kepler 1658b's orbit is actually decaying. It's spiraling inwards.
And whole systems can be extreme too. Kepler 90 has 8 planets tied with us. TRAPPIST-1 famously has maybe 4 planets in the habitable zone.
And then there's HD 11-Thursday-67 with 6 planets locked in perfect orbital resonance, like a perfectly choreographed cosmic dance. It's beautiful mathematically.
So, okay, with all this mind-blowing diversity,
Yeah.
it brings up the life question again, especially with things like those Hyson planets the Cambridge researchers found.
Right, Dr. Madhusudan's work. These are hypothetical planets, hydrogen-rich atmospheres over deep global oceans. The thinking is life needs liquid water, right?
Generally, yeah.
These planets could have vast amounts of it. Even if they're bigger and warmer than Earth overall, the conditions deep in those oceans might be stable, potentially habitable. Maybe life could use chemical reactions down there, chemosynthesis, instead of sunlight.
So life could exist in places really different from Earth.
It really broadens the possibilities, and some might be tidally locked, too.
Meaning one side always faces the star.
Yeah, perpetual hot day on one side, perpetual frozen night on the other. The habitable zone, if there is one, might just be in the Terminator zone, that twilight strip between the extremes.
No day-night cycle, no seasons. Maybe no starry sky on the day side. So strange to imagine.
It forces us to shed our Earth-centric biases about what a living world should look like.
Which leads back to that big persistent question. If there's so much potential variety, where is everybody? Why haven't we found aliens, or why haven't they found us?
And the sources, like the quote from NASA scientist Dr. Amitabh Ghosh, bring us back to a stark reality. Space is just unbelievably big. The distances are almost incomprehensible.
How big are we talking?
Our fastest spacecraft, Voyager 1, has been traveling for over 45 years. It's now about 1 light day away. That sounds like a lot, but...
But the nearest star system, Proxima Centauri, is over 4 light years away.
Exactly. To get there with Voyager speed would take, well, tens of thousands of years. To cross interstellar distances generally, we're talking millions of years at current or near future speeds.
Millions of years just to reach the neighbors.
Yeah.
That really puts the silence in perspective, doesn't it? It's a huge barrier.
It's perhaps the biggest barrier we face for interstellar contact or travel, the tyranny of distance.
Okay, wow. Let's take our final turn into maybe the deepest, most abstract part of this. We've talked about moving through time and looking across vast distances in space. But what if time itself isn't what we think? What if it's not fundamental?
Yeah, this is the problem of time in physics. It's a really fundamental puzzle, highlighted in several sources. And the core issue is a clash between our 2 best theories of the universe.
Quantum mechanics and general relativity.
Exactly. Quantum mechanics, the physics of the very small, usually treats time as this fixed, absolute background stage on which events unfold, like a universal clock ticking everywhere.
Okay.
But general relativity, Einstein's theory of gravity and the large-scale universe, sees time completely differently. It's flexible, it's relative, it can be warped by speed and gravity, and it's interwoven with space into a single entity. Space-time.
So the theories disagree on the basic nature of time.
Profoundly. And when physicists try to unite them into a single theory of quantum gravity, the holy grail, this conflict about time becomes a massive roadblock. Is time fundamental? Does it emerge from something deeper? Is it even real in the way we experience it?
And some of those attempts to build quantum gravity, like the Wheeler-DeWitt equation mentioned,
Yeah.
they seem to make time disappear.
That's one of the strangest outcomes. In some of these mathematical frameworks, the variable for time just drops out of the equations describing the universe as a whole. The universe's fundamental state looks static, timeless. It's called the frozen formalism problem.
But that makes no sense with our experience. We clearly experience time flowing, things changing. How can the universe be fundamentally timeless?
Right. That's the huge disconnect. So how do we get from a potentially timeless fundamental reality to our everyday experience of flowing time? The sources outline a few really interesting ideas.
Like what?
One major idea from physicists like Page and Wooters is that time is emergent. It's not fundamental, but it appears to flow for observers inside the system, like us.
How does it emerge?
Through quantum entanglement. The idea is that the universe as a whole might be in a static, timeless state, but different parts of it are entangled with each other. Time emerges as a way to describe the relationships and correlations between these entangled subsystems, including things we use as clocks.
So time is relational. It arises from how parts of the universe interact.
That's the concept. There was even an experiment with entangled photons that seemed to show this. From an external perspective, looking at the whole system, it was static. But from the internal perspective of one photon relative to the other, acting as a clock, time seemed to emerge and flow.
Wow, okay. That's one possibility. What else?
Another perspective put forward by researchers like Amrit Sorli and Stefan Salin goes even further. They argue that what we call physical time duration, the flow from past to present to future, isn't a fundamental dimension at all.
So what is it then?
They suggest it's an emergent physical quantity that only really comes into existence when measured by an observer, like using a clock.
So if you don't measure it, it's not there.
In a physical sense, yes. In their view, change and motion happen fundamentally in space, which itself is time invariant, timeless. The universe just is constantly changing in this timeless space.
So where does our feeling of past, present, future come from?
They propose that's psychological time or neuronal time. Our brains construct this linear sequence to make sense of sensory input and memory. It's a product of consciousness, not a fundamental feature of the cosmos. Without measurement or conscious observation, there's just change in space.
So entropy increasing, the arrow of time that's happening in space, not over time.
That's their argument, yes. Entropy increases within time invariant space. Causality becomes a model we impose. And fundamental time might just be the numerical order of discrete changes, like ticks at the Planck scale.
What does that view mean for things like, well, entanglement or the block universe?
They argue it resolves the EPR paradox because entanglement happens instantly in time invariant space. It has no duration, and it directly contradicts the block universe idea.
Where past, present, future all coexist.
Right. In their model, only the present, this timeless space where change happens, is physically real. Past and future don't exist out there somewhere. They connect this to Einstein's feeling that the past-present-future distinction is an illusion, suggesting maybe he was tapping into this idea of timeless cognition.
Time travel.
Categorically impossible in this model. If motion only happens in space and time isn't a physical dimension you can move in, then there's nowhere to travel to in time. It simply doesn't work.
They also challenge the idea of curved spacetime.
They argue that the 4D spacetime of general relativity is a powerful mathematical model, but not necessarily physical reality. Time, having no physical existence in their view, cannot be curved. They point to measurements suggesting the universe is flat on large scales as potentially supporting this. It aligns with Hawking's conjecture against time travel and even Gödel's later doubts about time and relativity.
The radical perspective.
Yeah.
Is it widely accepted?
Oh, definitely not universally accepted. It's one viewpoint in a very active, ongoing debate. Other physicists, like Smolin or Ravelli, have different ideas about objective time emerging from scale or thermodynamics. It's very much an open question.
So going back to something like time dilation near a black hole, how does that fit if time isn't real in this fundamental way?
Well, time dilation is definitely a real, measured effect predicted by relativity. Clocks do run slower in strong gravity. Within an emergent time view, like Sorley and Seelan's, you might interpret this not as a fundamental river of time slowing down, but as the rate of physical change or material processes slowing down in that region. A clock measures this rate, duration, and it's slower relative to a clock far away where processes run faster. Space-time curvature and frame dragging are still real effects of mass energy on the geometry of space, but the interpretation of the time component differs.
It seems like our own perception really shapes how we think about this.
Hugely. The NASA source points out our brains are wired to create that narrative of time flowing. We sequence events, create before and after from sensory input and memory.
It's how we function, how we survive.
Yeah.
Predicting the future based on the past.
Exactly. Which makes it incredibly difficult to intuitively grasp a reality that might be fundamentally timeless, even if the physics seems to be hinting at it.
So the big debate continues. Is time a fundamental dimension, the block universe? Or is it emergent, a construct, maybe an illusion created by change, entanglement, and our own minds? Time dilation proves something is happening, but what it tells us about the ultimate nature of time
is still one of the deepest mysteries in physics and philosophy, not settled at all.
What a journey. Okay, so wrapping this up, we started with the sci-fi dream of time travel, finding that physics seems to allow trips to the future via relativity.
But slams the door pretty hard on traveling to the past, at least with current knowledge.
Then we leaped across the cosmos to marvel at the sheer extremity and diversity of exoplanets, reminding us how weird and wonderful the universe is.
And keeping that hope alive, maybe, for finding life in places utterly unlike Earth.
And finally, we plunged into the really deep end, grappling with the possibility that our most basic experience, the feeling of time flowing, might itself be an illusion or something emergent.
Arising from change or quantum connections in a universe that, at its deepest level, could be fundamentally timeless.
It really covers an incredible spectrum, doesn't it? From real gravitational effects to the very nature of reality.
It certainly does. Lots to chew on there.
Absolutely. So for you listening, what stands out after hearing all this? Does thinking about time, maybe not as a river, but as a measurement of change, does that shift how you see the world? It definitely gives you something different to consider the next time you glance at a clock.